In today's world of high-performance computing, how processors access memory is a critical factor in system design. Two major architectures dominate this space: uniform memory access, or UMA, and non-uniform memory access, known as NUMA. Understanding the differences between these two approaches is essential for anyone interested in computer organization, server design, or optimizing software for multiprocessor systems. In this video, we'll break down what UMA and NUMA are, how they work, their advantages and disadvantages, and where each is best applied. Let's start by exploring the basics of memory access in multiprocessor systems. Uniform memory access, or UMA, is a memory architecture where all processors in a multiprocessor system share the same physical memory and have equal access time to any memory location. This means that no matter which processor requests data, the latency and bandwidth are consistent across the system. UMA is typically implemented using a single memory controller and a shared memory bus, making it straightforward to design and manage. This architecture is common in small-scale systems like desktop computers and low-end servers, where simplicity and cost-effectiveness are important. In a UMA system, all processors are connected to a single shared memory pool via a common bus or interconnect. This setup ensures that every processor experiences the same latency when accessing any part of the memory. The memory controller manages all requests, and the bandwidth is divided among all processors. While this design is easy to implement and manage, it can become a bottleneck as more processors are added, since they all compete for the same memory resources. Let's look at the main types of buses used in UMA: single, multiple, and crossbar. UMA offers several key advantages. First, it's easy to implement, making it ideal for small-scale systems. All processors have equal access to memory, which simplifies programming and system management. UMA also provides low latency for memory access, ensuring that processors can retrieve data quickly. Additionally, the architecture is cost-effective, as it requires only a single memory bus and controller. These benefits make UMA a popular choice for general-purpose and time-sharing applications, where simplicity and predictable performance are valued. Despite its simplicity, UMA has notable limitations. As more processors are added, they must compete for the same memory bus, leading to contention and reduced performance. The shared bus also limits the total bandwidth available, which can be a problem for memory-intensive applications. Furthermore, the total memory capacity is restricted, since all processors share a single memory pool. These factors make UMA less suitable for large-scale or high-performance systems, where scalability and bandwidth are critical. Non-uniform memory access, or NUMA, is a memory architecture designed to overcome the scalability limitations of UMA. In NUMA systems, each processor is connected to its own local memory, and these memory modules are interconnected. While a processor can access both its local memory and remote memory attached to other processors, access to local memory is much faster. This design allows NUMA systems to scale efficiently, supporting more processors and larger memory pools, making them ideal for high-performance and real-time applications. In NUMA systems, each processor has its own dedicated memory controller and local memory. These memory nodes are interconnected, allowing processors to access both local and remote memory. However, accessing local memory is much faster than accessing memory attached to another processor. This non-uniformity in access times is the key feature of NUMA. The architecture is well suited for workloads that can be divided among processors, minimizing the need for frequent remote memory access and reducing contention. NUMA brings several important advantages to multiprocessor systems. By providing each processor with its own local memory, NUMA reduces memory access times and improves overall system performance. The architecture is highly scalable, allowing additional processors and memory nodes to be added as needed. NUMA also helps reduce memory contention, since processors primarily access their own local memory. These features make NUMA ideal for real-time, high-performance, and time-critical applications that demand both speed and scalability. While NUMA offers significant benefits, it also introduces complexity. Designing and implementing NUMA systems requires specialized hardware and software to manage memory access and maintain data consistency. This added complexity can increase costs compared to UMA systems. Additionally, if a workload requires frequent access to remote memory, performance can suffer due to higher latency. Therefore, NUMA is best suited for applications that can take advantage of local memory access and minimize remote memory usage. Let's compare UMA and NUMA side by side. UMA uses a single memory controller and provides equal access time to all memory locations, but struggles with scalability and bandwidth. NUMA, on the other hand, uses multiple memory controllers and provides faster access to local memory, supporting better scalability and higher bandwidth. However, NUMA systems are more complex and can experience performance variability depending on how memory is accessed. The choice between UMA and NUMA depends on the specific needs of the application and system size. In UMA systems, three types of buses are commonly used: single, multiple, and crossbar. These buses connect all processors to the shared memory pool. In contrast, NUMA systems typically use tree or hierarchical bus structures to connect memory nodes and processors. The choice of bus architecture impacts system performance, scalability, and complexity. Understanding these bus types helps in designing systems that balance cost, performance, and scalability according to application needs. UMA architectures are best suited for general-purpose and time-sharing applications, such as desktop computers and low-end servers, where simplicity and predictable performance are important. NUMA, on the other hand, excels in real-time and time-critical applications, such as high-performance servers and scientific computing, where scalability and fast local memory access are essential. Choosing the right architecture depends on the workload, system size, and performance requirements. Some well-known examples of UMA systems include Sun Starfare servers, Compact Alpha servers, and HPV series. These systems use a single memory controller and are designed for environments where simplicity and cost are priorities. NUMA systems, such as those built by Cray, TC2000, and BBN, are engineered for high-performance computing, supporting many processors and large memory pools. These examples highlight how different architectures are tailored to specific computing needs. Let's quickly review some key points with a short quiz. Which statement is true about memory access in NUMA? The answer: local memory access is faster than remote. In UMA, adding more processors eventually leads to memory bus contention. NUMA's main disadvantage is higher complexity and cost. UMA uses three types of buses: single, multiple, and crossbar. NUMA is best suited for real-time and time-critical applications, and generally offers faster memory access than UMA due to local memory optimization. To wrap up, both UMA and NUMA play vital roles in modern computing. UMA offers simplicity and predictable performance for smaller systems, while NUMA provides scalability and high performance for demanding, large-scale applications. The choice between them depends on your specific needs, including workload type, system size, and budget. By understanding the strengths and limitations of each architecture, you can make informed decisions when designing or selecting multi-processor systems. Thanks for watching, and keep exploring the world of computer architecture.